Okay, welcome Organic Chemistry 2331. We're going to continue on with chapter 6. Let's recap what SN1 is. It's a concerted reaction. It happens all at one time. We're making and breaking bonds all at the same time. We get inversion of stereocenters because it has to come in from where the leaving group is, the opposite end from where the leaving group's leaving, and that flips it over. We see that the type of alkyl halide affects the reaction. The methyl and the primary go faster. Secondaries can do SN2 reactions, but tertiaries can't. Tertiaries can't. There's just too much steric demand. They cannot do that reaction. So that means we have to have a different reaction for tertiary alkyl halides. And we do. It's called the SN1 reaction. In the SN1 reaction, we have it done in 2 steps. So it's going to be a first order rate law reaction, okay? And so the 2 steps are: 1, we break apart the carbon and halogen bond to create a positively charged carbon. And then that positively charged carbon can be attacked by poor nucleophiles, things that don't have a negative charge, that only have a lone pair. So it actually gives us an opportunity to do some interesting other chemistries as well. So the slow step is this breaking of the bond. Now notice this is in equilibrium because bromine is a nucleophile. It's not a very good one, but it's a nucleophile. And so it can attack there and go back to the starting material. So in this case, we've done it where we created 1 molecule has to break apart into 2. So that means it's a unimolecular reaction, okay? Only takes the one, only the concentration of the alkyl halide. So that's why we call it a substitution reaction, a nucleophilic reaction, but it's a 1, unimolecular, okay? SN1 reactions always form this carbocation, this plus charge on carbon. Now in this case here, it's also always the slow step. Once you form this carbocation, it's very reactive and react with lots of things, and those tend to be very fast steps. In fact, in this case, we're reacting with neutral water. And neutral water is using a lone pair set of electrons to make that new bond with carbon, and therefore we're ending up with a positive charge on oxygen. Luckily, we have a hydrogen, and we could just remove a hydrogen to remove that positive charge. In fact, water right here is acting like a Bronsted-Lowry base and taking that proton away, giving us our neutral product. Okay, so substitution, nucleophilic, unimolecular, SN1. Okay, so let's talk about reactivity on substrate. We saw that in SN2s, methyls and primaries reacted fast, secondaries reacted slower, and tertiaries didn't react at all. But in SN1 reactions, it's opposite. Turns out that tertiaries react the fastest, secondaries do react, and primaries and methyls hardly ever react at all. So now we have a reaction mechanism that's substrate almost dependent, except for our secondaries. So our alkyl halides undergo these very rapidly. These do not, methyl and primary do not undergo these, okay? So what's so different? In the other reaction, we had the unimolecular, the bimolecular reaction, where you had to have the nucleophile coming opposite where the leaving group was going to leave. Here we have the leaving group has already left. So why is the tertiary so much faster than a secondary, and why don't the methyl and the primary react? Well, I'll keep you on that cliffhanger while we take roll. Everybody at home, don't forget to take the quiz. It's hard. Study good. Study well, sorry. All right. Phones have gone down, so we'll go. Okay. the reason we have this is we actually want to look at that stability of the intermediate we formed, okay? We're looking at that stability of the intermediate we formed. To get to this stage, we have to have our one molecule has to break a bond. So we have to put a lot of energy into this to break that bond. But when we break that bond, we don't go to products immediately. We go to an active species right here. And then that has to have a second activation energy to react with the nucleophile. And after that happens, then it cascades down to products. And in this case, we have an overall exothermic reaction. We have two steps in our reaction, and we formed an intermediate, okay? You always form a carbocation in an SN1 reaction. Okay, so there has to be something about the stability of this intermediate here that lends itself to being so much faster than other things. So as it turns out, we actually have a weird trend here. The tertiary carbon is the most stable carbocation. And then the secondary is pretty stable. And then these two right here are not very stable at all and hardly ever get made, okay? Hardly ever get made, okay? So why? Why does this happen, okay? Well, it turns out we have two different properties here that are helping us make this stability trend. The tertiary is more stable because it has some inductive effects that we saw when we talked about acid strength, okay? So let's look at the tertiary right here. We have this right here. It has carbons bonded all the way around it. Now that the carbon has a positive charge, it wants to pull electron density in from each of these carbons. As it does so, it's no longer a full positive charge. It's only part of a positive charge, okay? So this inductive effect, pulling it through the bonds, means that anytime you have a carbon or a more electronegative atom, it can pull electron density away from it and make it more stable. But let's look at what a secondary is. Secondary, yeah, okay, great. It gets some of that inductive effect, but the hydrogen can't do anything. It has a full S1 orbital. In its really small orbital, it's not going to share any of those electrons. So it can only draw from two of them, making it less stable. So this is less positive than this because it's drawing another carbon into that positive charge. Okay, so then let's look at a secondary. In the primary case, we only have one carbon and two hydrogens, which are basically useless for induction. And so we see that it is less stable than the secondary. And then, of course, the last one would be the methyl cation, which is the worst because that's a full positive charge on carbon. There's no inductive effect at all stabilizing that and making it the least stable. Okay, so it also should probably have the highest activation energy to make because it's the least stable. Okay, so that's the first effect. Okay, the second effect is what we call hyperconjugation. But to understand hyperconjugation, we got to understand the shape of our carbocation. Okay, our carbocation has changed hybridization from sp3 when it was bonded to the halogen to sp2. So it's sp2, and it has one p orbital, and it's empty. Okay, so if that carbon is sp2, that turns it back into trigonal planar, and we have that p orbital above and below the plane of that trigonal planar shape we got. Okay, so what can happen is we can actually have the sigma bond between the hydrogen and the carbon line up fairly close to that empty p orbital. And when it does, one of the three, this one can't and this one can't, but one of the three can line up with that p orbital and donate some electron density, further stabilizing that positive charge. So the inductive effect is directly through the bonds, and the hyperconjugation is through space with one of the carbon-hydrogen sigma bonds. Okay, so if we look at it from an idea of, well, how can we see that stabilization going on? Well, we have our inductive effect now 3 times, but now we can also hyperconjugate one of each of these hydrogens. So now we have 6 different things helping stabilize that tertiary cation. Okay, in the isopropyl, we can only do that twice on the 2 sides, only 4 things stabilizing that cation. Over here, we have 1 and 1, only 2 things stabilizing that primary cation. And when we go to our methyl cation, there's nothing stable at all right here. In this case here, we have, it's a primary with hybridization. And in this state here, we have, again, primary with only the 2 stabilization. Methyl has, the methyl has none. The hydrogens don't contribute anything for hybridization, hyperconjugation, or for induction. Okay, so do we understand why the tertiary carbocation is the most stable? Okay, that's great. So this trend will go for all through your chemistry. Okay, now that we know that the carbocations are more stable, we have to understand the problem with carbocations. The carbocations rearrange. Okay, if you have a secondary carbocation, it will rearrange to a tertiary carbocation. It wants, there's that much energy saved to be able to just move a bond over 1 carbon. And it only moves over 1. We call it a 1,2 hydride shift. Okay, the reason we call it a hydride shift is the hydrogen actually takes the electrons with it. When it moves, it takes its electrons with it. This right here, a hydrogen with 2 electrons in its outer shell is called a hydride. It's a full shell, but it has a negative charge. Okay, so we're going to move a hydrogen 1 over. We only do it to make a secondary or a tertiary. Only do it from a secondary to a tertiary, not the way back, not the other way back. So how do we know this kind of happens? Well, turns out if we run a reaction and influence it to go under SN1 conditions, the first step in an SN1 reaction is carbocation formation. Now, if a carbocation can rearrange, it will. So what happens is, in this case here, we started with a secondary bromide, okay? And so we heated it up or something and broke that bond to form that carbocation, okay? Now this carbocation is on a secondary carbon, but look, this carbon right next to it is a tertiary carbon and it has a hydrogen on it. So what it's going to do is the hydrogen is going to take its electrons and move over here to give us our tertiary carbocation. Okay, it went from a secondary carbocation to a tertiary carbocation by moving that hydrogen and its 2 electrons. Now that we have this tertiary carbocation, it's going to react with water. And after it reacts with water, it's going to give us our alcohol here. Now notice it's giving us our tertiary alcohol. Okay, so first step is carbocation formation, then the nucleophile can react with it. Of course, it's going to rearrange first, so you got to plan for that. And then we can get our alcohol out of it. But if we, instead of using water as our solvent, water as our nucleophile here, what if we used a strong nucleophile? It's a secondary, so it can undergo SN2 reactions, it's just slow. And we have a strong nucleophile, so it's going to react with an SN2. Strong nucleophile says SN2. So what's going to happen is we're going to displace this bromide right here, and we're going to get a secondary alcohol. Same starting material, 2 different products, 2 different mechanisms. Okay, so that is one of the things about our knowing our mechanisms and which one they are. They help us pick our products. Okay, so this is with hydrogen. Well, it turns out it can also do it with methyl groups. We can do that, and it's called a 1,2 methyl shift. In this case here, we have, again, a secondary alkyl halide, but this carbon is quaternary, so it can't move. But if we take this methyl group and its electrons and shift it over 1 carbon, that's going to give us a tertiary carbocation. And that tertiary carbocation is more stable, and therefore it's favored. And then we can then, of course, react it with a nucleophile, and in this case, giving us a tertiary alcohol. Okay. So this is the 1,2 methyl shift. Okay. So you can shift hydrogens and methyl groups one carbon over to make a more stable carbocation. Okay. So you need to look at it kind of and say, can it rearrange first? Okay. So we form this secondary carbocation here. And if we tried to do it one way, move it this direction, that would give us a primary. So that's not going to work because so we can't do that. And so we could do a 1,2 hydride shift on the other side. Actually, let me erase that. We could do a 1,2 hydride shift this way, right here. But what's the problem with that? It would create another secondary. It's not more stable. It's not going to move. It will not do it. No. If you're making a secondary, if you have a secondary and you make a secondary, it's not going to move. And it won't rearrange. Okay. So, well, we do have this tertiary carbon here, but notice it's not on the second carbon over, it's on the third carbon over. So we can't do that either. It's not going to shift more than one carbon. So that's not going to work either. So it only does a 1,2 shift only with hydrogens and methyl groups. Okay. And it's always to get the more stable things. The other way of doing it instead of moving just a methyl group is if you have small rings, like 3, 4, 5 membered rings, you can actually expand the ring by doing a methyl type shift. Okay. So what we have here, oops, that's not what I wanted, is we have a secondary alkyl halide. We're going to break that and create a secondary carbocation. Now, we could move this methyl group over here and do that, but the reason the ring expands is because of ring strain. That's why it's 3, 4, and 5 membered rings all have ring strain. It's more thermodynamic for the molecule to open the ring up a little bit more than it is to just move the methyl group. So if we do that, it's that new bond formed is right here, and it's all kind of weird. So let's redraw it here. So this is the equal, same thing. Now we have a tertiary carbocation in our ring. Now our nucleophile can do it. But again, we're looking at 3, 4, and 5 membered rings that are going to expand under this condition. What I like to do is I like to do what we did here, draw where the new bond is going, draw where the new carbocation is, and then redraw the structure after that to make sure that you have the connection going to the right atom. Okay, that's the best way to make sure you have the connection going to the right atom. Okay, so questions about the 1,2 hydride shift. Okay, so now we're going to do something a little different. We're going to talk again about that structure of the carbocation again and how it affects our products. Okay, so let's look at this structure again. Again, we have that sp2 hybridized carbon. We have a free p orbital. Half of that p orbital is above the plane and half of that p orbital is below the plane. Which lobe of that orbital is the nucleophile going to attack? The top or the bottom? The top? Okay. What's wrong with the bottom? No, the charge is spread out over both orbitals. In fact, the answer is yes, it's going to attack the top, but it's also going to attack the bottom an equal number of times because they're equivalent electronically. So whatever side your nucleophile came in on is the side it's going to attack. What does that do for our stereochemistry? It means if it attacks from the top, you're going to get one stereoisomer. If it attacks from the bottom, you're going to get the other stereoisomer because your 3 things have to flip up to go back to that tetrahedral shape. So what we call this is, in the case here, once we go through this planar carbocation, you get both isomers of it in equal portions. So you get half R and half S. And when we talked about R and S in the last chapter, we said if you had a mixture, a one-to-one mixture of R and S, that was called a racemic mixture and was not optically active. So our SN1 reactions always produce a racemic mixture if there is a chiral center. We call that process racemization, making a racemic mixture by using that carbocation. And remember, SN2, we got stereo inversion. We were stereo selective. In SN1, we get a mixture. We are not stereo selective. Okay? So do we see why, by looking at that shape of that carbocation, why we get half and half? Whichever side of the molecule the nucleophile comes from is where it's going to react. There's no preference at all. Okay. So I'm going to skip that, and I'm going to talk about this instead. Let's talk about the rate determining step in carbocations. Okay. And in the case of a tertiary carbocation, it has a lower activation energy and greater stability than a secondary carbocation. Okay, so in the case there, we can see that in this lower line here, we have a lower activation energy and a pretty stable, or more stable. It's less stable than our starting material, but it's more stable than a secondary. Okay, so that reaction is going to happen faster, and this carbocation is going to be more stable than the other one. Now let's look at our secondary. Our secondary is going to have a higher activation energy because it's a less stable carbocation. So it's going to form slower. So your tertiary alkyl halide is going to form a tertiary carbocation more readily than a secondary carbocation can form. And it's going to happen faster. Okay, so it's going to happen faster and be more stable. Okay, so now let's put this together. We have SN1 and SN2, two different mechanisms. And if we look at the products, we can see which mechanism it went by, because it'll either have a rearrangement or a racemization or different stereoisomers, or it'll have just one center inversion. So let's talk about ways to compare and contrast the SN1 and SN2. Okay. The first and most important thing to look at is your degree of alkyl halide. Is it a primary, secondary, or tertiary? Okay, or methyl. So look at that first. What is the alkyl halide? That's going to tell you a lot of the story right there. Okay, the second thing we're going to look at is the nucleophile strong or weak? Okay, we saw good nucleophiles have negative charges, poor nucleophiles have large bulky groups and or neutral, like water and methanol. Okay, and then the last thing we look at that can help decide yes or no, whether it's SN1 or SN2, is the solvent. Okay, the solvent effect. Is it in a protic solvent or an aprotic solvent? Okay, so we're going to use these rules and try to identify how we're going to get this. So the first and most important factor is, of course, the substitution on the alkyl halide. So we saw in the first set, last time, that the methyl and primary only do SN2. So if you were looking at a primary alkyl halide and I said, what mechanism is this going to go under? You're done. Only SN2. Okay. And then we learned today that the tertiaries right here don't undergo SN2. They only undergo SN1. And they do it very fast, and faster than a secondary. Okay. So that means if you have a tertiary, you're done. You know you're SN1. Okay, now the problem comes with your secondaries, because your secondaries can be either SN1 or SN2. So now we have to go look at that next piece of information. That next piece of information was strength of the nucleophile. Okay, so let's see how strength of the nucleophile affects our reaction here. Okay. So in the case of strong nucleophiles, those that already have the electrons ready to bond, you are more likely to undergo SN2 reactions. Strong nucleophiles will undergo SN2 reactions. They favor SN2 reactions. Okay, why? Well, you only have a little bit of sterics there, and you have a strong nucleophile, so it's willing to go in and look for that partially positive carbon on that polar bond to make it happen. Weak nucleophiles, on the other hand, aren't very strong, can wait around for that carbocation to form, and therefore they favor SN1 reactions. Okay, so they favor SN1 reactions. And so if we looked at this alkyl halide right here, it's a secondary alkyl halide, and we said, well, gosh, you know, I want to make an alcohol out of this, so I'm going to hit it with a strong nucleophile, the OH here, hydroxide ion. Okay, and we know that when we have a strong nucleophile, it's going to come in from the backside here and give us one stereoisomer. Our SN2 is going to give us one stereoisomer, and we get one product here. We get our trans methyl cyclohexanol. Okay, it was cis bromo methyl cyclohexane, and now because of inversion, it's now trans right here. But if we didn't want to hit it with something like that, and we just wanted to boil it in water, water was the nucleophile, what would happen would be it would form a carbocation right here, and then half of the waters would attack from the top and form an alcohol, and then the other half would attack from the bottom and form an alcohol. So we'd actually get two isomers from this. We'd get the cis and the trans isomer in equal portions. Okay, so if we ran the reaction and we only got the trans isomer, we knew we were going to have it through an SN1 reaction. If we got a mixture of isomers or racemized it, it will be 2. This actually isn't a stereocenter, but it is a stereo, the ring has stereochemistry to it. Okay. Okay, does that make sense? Strong nucleophiles are fast, so they're going to favor SN1. They don't have to wait for that carbocation to form. Weak nucleophiles are slow. They have to wait for the carbocation to form. And then they react rapidly. Okay, so then the last thing is solvent effect. Okay, remember when we talked about solvents like water, protic solvents change the order of reactivity of the halide series because of how they balance the charge, right? Water can hydrogen bond to negatively charged things, but it also has lone pairs to bond to positively charged things. So polar protic solvents can solvate both anions and cations. So if a polar protic solvent is solvating a cation, polar protic solvents favor SN1 reactions. It's solvating that carbocation. Polar protic solvents favor SN1 reactions. In fact, SN1 reactions are increased in rate in polar protic solvents. Okay, in polar aprotic solvents, they favor SN2 reactions because they want the nucleophile to not be well solvated. They want as much of that negative charge there as possible because that negative charge is going to influence it to go out and react. It's going to give it the kinetics there, okay? And so SN2 reactions are dramatically increased in polar aprotic solvents, okay? So polar protic solvents, SN1. Polar aprotic solvents, SN2. Okay, so now we have 3 pieces of information that we look at when we're looking at what kind of halide do I have? Okay, we know where that is. What kind of nucleophile do I have? And now what kind of solvent do I have? That should be the last thing you need to say absolutely positively. It's SN1 or SN2. Okay, so the leaving group itself doesn't affect the mechanism. However, the leaving groups have an order of reactivity. The iodine is the longest bond and most polarizable bond, and therefore it is going to come off first. It's also the strongest acid. It has the strongest conjugate acid, meaning it's the weakest conjugate base. So it's going to take its electrons and be happy. Okay. So then bromine is next, chlorine and iodine for the same, or we're decreasing bond length and we're increasing bond strength. So decreasing bond length and strength means that we're going to see faster reactions with iodine and bromine than with chlorine and fluorine. But it's either mechanism works in there. So it doesn't, the leaving group has no effect on the mechanism, just the rate. Okay, now I want to introduce these here because these are going to come up pretty soon about looking at things. And so if we have a halogen bonded directly to a vinyl group or a benzene ring here, these carbons are sp2 hybridized. Do they undergo SN1, SN2 reactions? No, the requirement for an SN1, SN2 reaction is it must be sp3 hybridized. Starts sp3 hybridized and it ends sp3 hybridized. You know, the carbocation is sp2 hybridized, but we reacted it, okay? So because of that, these cannot undergo SN2 type reactions. However, if we have them close to a carbon that is there, they actually can participate. And these are called benzylic, which is the CH2 is spacing it there. And this is allylic right here. So it's one off of it. So our halogen is here. This is a primary allylic, okay? So what is so special about these? Well, remember when we talked about hyperconjugation with the methyl group and the hydrogen carbon bond? Well, if we form our carbocation, we're going to have our carbocation here. But look at this, we already have a p orbital here and a p orbital here. We have real conjugation, full conjugation with that carbocation, which makes it stable, makes it more stable. And so these are actually more stable and more reactive than our tertiary alkyl halides. Now in the benzene ring, we also have a whole, 6 whole p orbitals in our benzene ring over here. And so when we do form our carbocation, it's also spread out around that ring. So we have true conjugation. So both benzylic, which is 1 carbon away from there, and allylic, 1 carbon away from the double bond, actually react. Now, the tertiaries only react by SN1 because of sterics, but these can react by SN2 as well. So, but notice that we have a primary and the secondary allylic halides can react in SN1. It's the only primaries that will react by SN1. The only reason it works is because of this conjugation, okay? So how are we going to change which mechanism we use for the primary and secondary allylics? We change the solvent. We want a SN2 reaction, we run it in a polar aprotic solvent. We want an SN1 reaction, we run it in a polar protic solvent. So just changing the solvent changes the mechanism for these allylic and benzylic halogens. Okay, questions on that? Okay, so we're going to summarize and help us predict this, okay? If our substrate is tertiary or a secondary that's big and bulky, you're going to make an SN1 reaction, okay? If the nucleophile is weak, you're going to probably have an SN1 reaction. If the solvent is protic, you could be a redneck. No, it's an SN1 reaction. Leading group, again, doesn't really matter. It's the same reactivity for both. SN2, methyl primary and small secondaries. Run it in a polar aprotic solvent and use strong nucleophiles or Lewis bases. Okay. So those are how you can influence these things in TIC. So the first thing you do is look at your primary, secondary, tertiary. Second thing you look at is my nucleophile strong? Third thing you look at, what's my solvent? By the time you have those three pieces of information, you should make a decision, okay? So let's change that summary and look at it this way. SN2 is one step bimolecular, one peak on our energy diagram. It cannot rearrange because it never forms a carbocation, and we always get inversion of the configuration. Even if it's not stereochemical, it gets inversion of the situation. And only methyls, primaries, and secondaries react. Some secondaries. SN1 happens in two steps, always forms a carbocation. Carbocations can rearrange. If you have a secondary carbocation, it will rearrange to a tertiary carbocation if it can. Okay, so always look for those rearrangements. We have racemization. We change the configuration completely. And it's mostly tertiaries and some secondaries. Okay, now if we add to that our vinylic and aryls, the vinylic, the one where the halogen is on the sp2 carbon, don't react at all. So that makes it easier. When you have the benzylic and alkyl halides, tertiaries are SN1 only. When you have tertiary alkyl halides, SN1 only. Two sterically hindered will not react by SN2, therefore it's going to make us form the carbocation. Okay, and then our primaries and methyls only give SN2. So that means the one that's going to give us a little bit of trouble is the secondary alkyl halide and the primary and secondary benzylic and allylics. They can undergo both mechanisms. And again, to force the mechanism one way or another, change the solvent or change your nucleophile. Okay. So that being said, we can use this one reaction, well, technically two. We can use these two reactions to make a wide variety of functional groups. If we use hydroxide, we're going to make an alcohol right here. Convert any alkyl halide into any of these functional groups. So it's really, really useful reaction. If you use an alkoxide, you'll make an ether. If you use the hydrogen thiolate here, you're going to get a thiol. And if you use the carbon-centered one, you're going to get a thioether. You can even use this one right here, cyanide ion. Cyanide ion is a good nucleophile. It's going to give us a nitrile and add a carbon to our carbon chain. We can even do the acetylide ion here. It's a strong nucleophile. It's got that nice negative charge. And we're going to make a carbon-carbon bond here and extend our chain. We're going to add carbons to our chain. If we use an acetate ion here, we're going to get an ester. Notice that the alkyl halide portion is going to be, if we clip this ester apart, it's going to be in the alcohol portion. So really, it's kind of like this reaction up here, but we get a different functional group, or ester. If we use a tertiary amine, we can get a quaternary ammonium salt. And if we use azide right here, we'll get an alkyl azide. Okay, so that means all of these functional groups can be made by this same reaction. All you have to do is change your nucleophile. Okay. Okay, and I want to stop there because of the next thing is going to be a little different there. So what I want to do is I want to actually draw some structures, and we're going to predict what kind of mechanism that they're going to undergo. Okay, so let me go there and blank here. So what I'm going to do is I'm going to draw a couple structures up here, and we're going to predict what happens. So I need to go to this pin. 1, 2, 3, 4. Let's put a bromine. No, going to put the bromine here. Okay, that's going to be our first structure. This is going to be our second structure. And this is going to be our third structure. Right here. Okay. So let's, by raising your fingers, what is this? Is it a primary, secondary, tertiary? Primary? Euler? Primary? Okay. So this is a primary. So what kind of reaction can it do? It can only do SN2. We're done. Boom. Yay. So this is a, let's see, 1, 2. This is a primary or secondary or tertiary. The next one over. It's a secondary. So we have we need more information because it can be SN1 or SN2. And let's look at our last one. It's a tertiary. So it can only do SN1. All right. So let's say we're going to react these, but we're going to react it with hydroxide right here. So what's going to happen with that? Well, for this one, we're just going to displace the bromine and create OH. Okay. And what solvent would we want to use in this to really force the hand, make sure it only did SN2? We'd want to use a polar aprotic solvent. So let's say we're going to use acetone right here. So the three things that made it go in that direction, oh, we got to erase this. There we go. That was the bond to bromine. The three things that told us it was going to do this was, number one, it was primary. Number two, we had a strong nucleophile, and we did it in a polar aprotic solvent. Okay, so let's do this one right here. What kind of solvent do we need to do this reaction in? Aprotic solvent. So we're going to pick methanol. MEOH and EOH. There we go. We're going to pick methanol because SN1 reactions are sped along by polar protic solvents. Okay, so we're actually going to use methanol as our nucleophile too. So what kind of nucleophile is methanol? It's a poor nucleophile because it doesn't have a negative charge, right? So now let's figure out what it's going to make as its product. It's going to be, let's see, that, and we're going to put an O, and then there's going to be a methyl group here, and then there's going to be a hydrogen and a positive charge. That's what happens first, because the lone pair on the methyl group is going to attack the carbocation. And then we're going to have something act as a base and remove this to give us our tertiary ether. So we're getting this tertiary ether. Okay, and that's our only product. Okay, if there was stereochemistry, which there isn't, we would have a mixture of the two products, but we have two methyl groups there. So let's do that same kind of thing here. If we took this one and had OH in acetone, right here, what would the products be? And we're going to do it again for methanol over here too. So if we did OH, what kind of reaction mechanism would it undergo? Strong nucleophile, polar aprotic solvent, SN2. So we're going to go SN2 here, which means we're only going to substitute. So our product is going to be one thing and one thing only, the OH, this alcohol. Now, it turns out that is a stereocenter, and so we're only going to have one isomer. Okay, so let's look at this one here. Okay, So if we're doing it in methanol, that's a polar protic solvent and it's a poor nucleophile, we're forcing it SN1. Okay. So let's draw that first product in SN1. You get a carbocation right here. What's going to happen? It's going to rearrange. It's a secondary carbocation. It's a secondary carbocation. It's not as stable as a tertiary carbocation. We have a hydrogen right here. We have a tertiary carbon right next to it. It can do a 1-2 shift to make a tertiary carbocation. So it's going to. And that hydrogen comes up over here and our carbocation's here now. And then that center is the one that's going to react. And so we end up with OMe and that. Oops, there. And we now only have one isomer because those methyl groups are the same. But notice it's the exact same product as if we did it with the tertiary alkyl halide. And it's all because of the stability of that carbocation. That stability of that carbocation, that 1-2 shift. Okay, do we see how to use the type of alkyl halide, the type of nucleophile, and the type of solvent to decide whether we're going to do SN1 or SN2? Okay, so go do your homework problems on it and do that. I'm going to stop here. We're going to do elimination with the next chapter anyway. So I'm going to stop here. Have a safe spring break. Please come back to me safely. We have a lot of learning to do, and I'd like to teach it to you. Okay? All right. Everybody at home, that goes for you guys too. Okay? All right. I'm going to go ahead and stop sharing.
What are the homeworks? So homework chapter 6 is due
Friday. Because we just finished most of it. Okay. All right. I'm going to stop recording. Homework for chapter 6 is